Okay, so after looking at normal metals and metallic bonding, there's a little bit more focus in the HL unit on transition metals. And I think we introduced this a long time ago, but a transition metal, the definition of a transition metal is that it's an element with an incomplete D sublevel in one or more of its oxidation states. Okay, so what does that mean? Well, if we think back to the periodic table, we know that there's a D block. D block is that sort of low, wide section of the periodic table. But not every element in the D block is a transition metal. So this whole section here in purple that I'm drawing, that represents the D block. And the D block is organized separately because the elements there are filling d orbitals. The d sublevel is the 5 d orbitals. And so an atom can have up to 10 d electrons in a given d sublevel. So to be empty in the d sublevel is not characteristic of a transition metal, or to be full in the d sublevel. So to have all 10 d electrons doesn't make something a transition metal. But in one or more of the oxidation states, it has to be incomplete. So that could mean 1 d electron all the way up to, there's 5, 6, 7, 8, and 9. So long as an element has from 1 to 9 d electrons in one of its oxidation states, then it can qualify as a transition metal. So for this reason, zinc is technically not a transition metal. Zinc's 2 oxidation states are either neutral, where it has a configuration of 4s2 3d10, and it also forms zinc 2 plus ion, where its configuration is just 3d10. So in both of its oxidation states, it has 3d10. Therefore, zinc doesn't qualify as a transition metal. It's a D block metal, but not a transition metal. Copper, on the other hand, although it starts out with 3d10, 4s1, 3d10, copper actually does qualify as a transition metal. It has 2 other oxidation states, copper 1 plus and copper 2 plus. And so it's copper 2 plus that qualifies copper as a transition metal, because that's its only oxidation state where it has an incomplete D sublevel. In the other ones, it has a full sublevel. So that's the definition of a transition metal. And when I use the term oxidation state, for now, we can think of that more or less as meaning a charge. It's not actually going to be a charge. We can assign oxidation states even when these elements are involved in covalent bonding. An oxidation state is a little bit broader of a term than just a charge. So they don't have to be true ions. We can still refer to them as being in certain states, acting as though they are +2, +3, +4 charged ions, even when they're actually sharing electrons. So that's a topic that we'll look more at when we get into the redox topic. Now, transition metals have quite distinct properties from metals that are in the S and the P block. And actually, their properties are a lot more metallic in terms of what we really think about as metals in our everyday lives. When you think of the metals that you see around you, whether they be the metals that are used in jewelry, the metals that are used to build things, the metals that are used in appliances, those things are largely composed of iron, nickel, copper, silver, gold, platinum, those types of things, with other elements mixed into them. So we use a lot of alloys in everyday life, and those are probably what you're familiar with. And so the reason that transition metals are distinct from the S and the P block elements, it has to do with those d electrons. Those d electrons are inner shell electrons. That's going to affect their sort of effective nuclear charge and some of their periodic trends. But those d electrons can also be involved in metallic bonding. So transition metals have much stronger metallic bonding than the S and P block metals, and it gives them more useful properties like high electrical and thermal conductivity, high melting points. They are malleable, yet they are strong. So speaking of periodic properties, the reason why the transition metals have these unique periodic properties has to do with those d electrons once again. So if we look back at a topic from the periodic trends unit, first ionization energies, it should stand out to you. If you look at row 1, they climb quite a bit, and the reason for that was that from hydrogen to helium, we have an additional proton in the nucleus of helium, which exerts additional nuclear attraction on the electrons. So the electrons get more attracted to the nucleus, and therefore it takes more energy to remove the electron from helium. And that same basic trend is seen across period 2. More protons leads to higher effective nuclear charge, higher attraction for electrons, more energy is needed to remove an electron from the atom. And it happens across row 3, across period 3. But then you get to row 4, which is the first time we have d electrons, and it sort of starts to climb here, and then notice that it just basically flatlines across the transition metals. Now, that's really weird. It hasn't done that up until that point. It's had these really steep increases, and again, you can notice that after the transition metals, it does another steep climb. But during the transition metals, first ionization energies more or less plateau. They climb a little bit, but not much. If you look at atomic radii, the trend is sort of reversed, that as we go from left to right, the atoms shrink in size. For that same exact reason, as we go to the right-hand side, we're increasing the number of protons. We're keeping the shielding effect the same because the number of inner shell electrons is not changing. And so if we do those two things together, we increase the number of protons, but we keep the shielding effect the same, then we see the effective nuclear charge go up. And if the effective nuclear charge goes up, we shrink atoms. We pull electrons closer to the nucleus. Now, you'll notice once again, if you look at the transition metals across period 4, the 3D, they more or less stay the same size. And you can see that that sort of repeats itself down here in the 4D, and it repeats itself again more or less in the 5D. So again, we have the transition metals really not showing the same degree of difference in their periodic trends that the S and the P metals do. And it has to do with the fact that those d electrons are inner electrons. So if I start off with an atom here, this would be calcium. Imagine that there's 20 protons in that nucleus. And there's 20 electrons arranged out here in the shells. Now, when I go to scandium, and so I add a 21st proton, I add another electron, but I actually add it here. So plus, here's that first d electron. So what that means is I've added a proton, which we know should increase the Z effective, but I've also added an electron to the 3D, and that you can see that's not on the valence shell. The valence shell is just these two pink electrons on the outside, the 4s. So I've added a proton, but I've also added an inner shell electron. So I've just added shielding effect. So I've added a proton, but I've also added shielding effect. And the added shielding effect reduces the Z effective. And so the net result is that the Z effective changes more or less cancel each other out. So if I then go to something that has 22 protons and 22 total electrons, again, now I've added 2 protons, but I've also added 2 extra shielding effects. I've added 2 inner shell electrons. And so has the Z effective changed? Not much. So the fact that as we go across the transition metals, for every additional proton, we add an additional shielding electron means that they have pretty much a constant amount of Z effective across the whole row of transition metals. And so that's why we see similar first ionization energies, similar atomic radii, it really gradually changing properties, gradually changing electronegativity, etc. Okay? And I believe we talked about this way back in the atomic structure unit, but similarly, as we remove electrons from transition metals, we see that it takes a very gradual difference in the amount of energy it takes to remove electrons from transition metals, unlike S and P block metals. So normally, in this topic, you talk about something. So this graph shows calcium. The first 2 electrons that we remove from calcium take a relatively low amount of energy. It does increase after we remove the first electron. We are at calcium plus, and so to take an electron from something that's positive takes more energy because the electron is now more attracted to that positive ion. But after the first 2 electrons off of calcium, we expect there to be a really big jump in terms of the amount of energy that it takes to remove the third electron from calcium, because the third electron from calcium is now in the lower third energy level. It would be a 3p electron instead of a 4s electron like those first 2. That's why we see those big jumps. But when we remove electrons from the transition metals, remember those 4s and 3d electrons are really, really close together in terms of their energy. And so what we see is that as we take away the first electron, so let's say we're now doing vanadium as is shown here. So vanadium is 4s2, 3d3. So we take that 4s electron, we take the next 4s electron, and then we take a 3d electron, and then we take another 3d, and then we take another 3d electron there. So with the transition metals, whoa, didn't mean to do that. With the transition metals, there's a very minor gradual increase in energy, or successive ionization energies, which is quite distinct from the S and P block metals. And so whereas calcium only ever removes these outer 2 electrons to become calcium 2+, it's never going to remove a third electron to become calcium 3+, because the energy difference, the amount of energy it takes to remove that third electron, is just too big an energy barrier. So it just doesn't happen. But with something like vanadium, it also has an ion where it loses those first 2 electrons, and you can get vanadium 2+. But then it doesn't take much more energy to remove the third, or the fourth, or the fifth. And so we also have oxidation states for vanadium where it's vanadium 3+, 4+, and 5+. So you can remove those outer 4s electrons, but then removing additional 3d electrons doesn't take that much more energy, and therefore allows all of these successive different oxidation states to form for these transition metals. So we can sort of justify all the different oxidation states that we see for transition metals because they show these gradual changes in their successive ionization energies. It only takes a little bit more energy to remove more and more electrons from the transition metals.